Hello guys, hope all of you are well in this difficult situation. Welcome to my lecture series. Let me introduce myself first. I'm Rinki Bhaumik, Assistant Professor, Department of Physics, JIS College of Engineering. Today's lecture is for first year. For first year, the paper name is Physics 1 and the paper code is EH101. The name of the paper is Physics 1 and 3 credits. There will be 3 lectures per week. Total 36 number of lectures will be there for all of you. This is for BTech first year as I said. Now let me show you your syllabus. This is your syllabus. First, this is module 1. In module 1, there is waves and oscillation. In module 2, there is classical optics where we have to discuss about interference of light and diffraction of light. In module 3, there is quantum mechanics 1 where we'll discuss about quantum theory and quantum mechanics. In module 4, there is solid state physics 1 where we'll discuss about crystal structure and semiconductors. And in the last module, that is module 5, we'll discuss about modern optics where there is laser and fiber optics. So this is your syllabus and these are some books which is recommended for all of you.
Welcome to another physics video. Today's topic is wave interference.
To interfere means to get in the way of something.
In order for waves to interfere, there must be at least two waves arriving at the same place at the same time. Suppose two wave pulses are traveling towards each other on a string. The diagram shows the situation. We can describe the wave pulses by their amplitudes. The blue pulse has an amplitude of 2 units and the red pulse, an amplitude of 1 unit. What will happen when the two pulses overlap?
Each pulse is trying to move the string outward, so if they both occupy the same place on the string it will go up even higher.
When the wave pulses overlap, they combine to make a new pulse, shown in green in the diagram.
To find the new amplitude, add the amplitude of the red pulse and the amplitude of the blue pulse.
In this case, the new amplitude is 3 units, 2 units from the blue pulse added to 1 unit from the red. Now suppose that the two pulses are moving towards each other, but one pushes the string up and the other pushes the string down, as in the diagram. What will happen in the situation when the two waves interfere, or overlap?
This time the blue pulse pushes up 2 units while the red pulse pushes down 1 unit, so I think it will still go up, but only 1 unit.
You are exactly right. The new wave pulse, shown in green, is 1 unit tall. Remember that wave amplitudes represent the displacement of particles, and displacement is a vector quantity. So, like we've done before, we will make upward displacements positive and downward displacements will be negative.
That is why the amplitude of the red pulse is shown as -1 unit in the diagram.
When the two waves both push in the same direction, we add the amplitudes to find the new wave amplitude.
And, when the two waves push in opposite directions, we still add the amplitudes as if they were vectors.
This rule, to find the new amplitude you add the vector amplitudes of the interfering waves, is called the principle of superposition.
Anytime that waves interfere, we can use the principle of superposition to find the amplitude of the new wave formed.
When the principle of superposition gives us a new amplitude that is larger than what we started with, we call the situation constructive interference.
But, when the interfering amplitudes combine to make a shorter wave, we call it destructive interference.
Now, let's suppose that we have two waves on a single string. One wave, the blue one, will travel to the left, and one wave, the red one, will travel to the right. Now let's add the sum of these two waves. The green wave shows what we would see on the string as the blue and red waves interfere. Now let's see what will happen as the two waves continue to travel. Now, let's watch again. This time pay attention to the black dot in the center of the green wave. Does it ever move? The point in the green wave represented by the black dot never moves. The blue and red waves always cancel each other at that point. Now watch the two peaks on the green wave. Pay attention to the left peak. Does the point on the wave with maximum displacement travel sideways, or straight up and down? The peaks travel up and down on the green wave. Because we can't see them moving left or right, this kind of interference is called a standing wave. The points with no displacement in a standing wave are called nodes. This wave has 3 nodes. The points in a standing wave with maximum displacement are called antinodes. This wave has 2 antinodes. Let's summarize. To make a standing wave, we need 2 identical waves traveling in opposite directions. The 2 waves should fit exactly on the string. When they interfere, they will produce a pattern that does not travel left or right but only shows motion up and down. The points on the standing wave that travel the greatest amount are called antinodes. The points that don't move at all are called nodes.
Antinodes are examples of constructive interference. And nodes are examples of destructive interference.
Today we'll do some numerical on interference. We had gone through the theory of interference. Now let's start the numerical. The first numerical you note down. Two coherent source. Coherent source what is you know already. two coherent sources of intensity watt per meter square. 10 watt per meter square and 25 watt per meter square. Interfere to form fringes. Find the ratio of maximum intensity to minimum intensity. So maximum intensity to minimum intensity, if we have to find, then there is a formula. The formula is I1 by I2 will be equal to A1 square by A2 square, which is equal to 10 by 25, because intensity 10, here 25, so that's why 10 by 25. Therefore it can be written as A1 by A2 equal to root over of 10 means 3.1623 divided by 5. If you do the square root, then we can get it. Now A1 equal to obviously 31.1623 divided by 5 in equal to A2 into A2. Now Imax by Imin is equal to A1 plus A2 whole square divided by A1 minus A2 whole square is equal to, if we do it, then finally what we can write, if you do the division, then the answer is 0.632. it can be like this. Okay, so therefore 0.632 into A2 plus A2 divided by 0.632 A2 minus A2, and there will be a square. So A2 obviously it will be gone. Now if we put these values in calculator, what we can get? Let's do it. So if you put on your calculator, then in the numerator you can get 2.664 divided by minus 1, so therefore 0.1351, so it will be equal to 19.724. so this will be the answer. This is the value of the ratio of maximum to minimum intensity. Now let's go to the next numerical. So the second numerical is, you first note down, in a double slit experiment a light of lambda is equal to 5640 angstrom is expected to slits which are 0.1 millimeter apart. The screen is placed the screen is placed 2 meters away from the slits. What is the angular position? Angular position means nothing but the theta of the 10th maximum and first minimum. So first you have to go through the problem. What is given that a double slit experiment, in a double slit experiment, which actually in the last class we already have derived the expression of the double slit. So double slit experiment, a light of wavelength lambda is given and also the distance is given. The screen between the screen and source, that is also given 2 meters away from the slits. What is the angular position of the 10th maximum and the first minimum? So therefore first we put all the values one by one. First lambda equal to 5460 angstrom. Now as we know that 1 angstrom equal to 10 to the power minus 10, so 5460 into 10 to the power minus 10 meter. 2D equal to 0.1 millimeter, that means 1 into 10 to the power minus 4 meter. Now the screen D equal to 2 meter. Therefore, we have to know the angular position. Now there is another formula, xn equal to n lambda capital D by 2 small d. This is the condition for maximum intensity. Condition for maximum intensity. This is the condition for maximum intensity. So, can we write it as x max, that is 10, because 10th is given. So, x max 10 is equal to 10 into, because n equal to here 10, lambda is given 5460 into 10 to the power minus 10 into 2, because d is 2. divided by 1 into 10 to the power minus 4 is equal to 0.1092 meter. So x 10th maximum now we know. Now we have to find out for 10th maximum angular position. So therefore phi maximum 10 is equal to x maximum 10 divided by capital D. So this is 10 actually, 10 phi maximum. This is the angular position. Therefore 10 theta maximum 10 is equal to 0.1092 divided by 2. So if you do, then clearly we can see that the value will be 0.0546 radians. So therefore the condition for minimum intensity xn 2n equal to 2n minus 1 lambda capital D divided by 4 small d. So the distance of the first minimum distance of first minimum x minimum 1 for first minimum will be equal to lambda capital D by 4 small d. So therefore lambda capital D by, if we 4d what we can write as 2 into 2 small d. So 2 small d we can write as 5460 into 10 to the power minus 10 into 2 divided by 2 into 10 to the power minus 4. Therefore finally the angular position of first minimum is equal to x minimum 1 divided by capital D. So it will be equal to 5460 into 10 to the power minus 6 divided by 2. So it is equal to, if we do, it gets 17. Oh, there will be 2 since so therefore the answer will be 0.00273 radian. This is the answer. So 0.00273 is the answer. So the angular position of first minimum is this. Now the third problem, let's do it. The third problem first you note down on your copy. In a Newton's ring, I hope you can remember. in a Newton's ring experiment, the diameter of the fifteenth ring was found to be 0.59 centimeter, and that of the fifth ring is 0.336 centimeter. If the radius of curvature of the lens is 100 centimeter, find the wavelength of light. So this is the numerical. First go through it. In a Newton's ring experiment, the diameter of the 15th ring was found to be 0.59 centimeter, and that of the fifth ring is 0.336 centimeter. So if the radius of curvature of the lens is 100 centimeter, find the wavelength of the light. Now how to do it? First, D15 it is given 0.59 centimeter. So therefore 0.59 into 10 to the power minus 2 meter. D next 5 is equal to 0.336 centimeter, which is equal to 0.336 into 10 to the power minus 2 meter. Radius of curvature which is R is equal to 100 centimeter. So now all these values we have to put in a formula. The formula is lambda equal to dn plus m square minus dn square divided by 4n into r. So if we put the values, then 1 by 1 0.59 into 10 to the power minus 2, that whole square, minus the another value is 0.336 into 10 to the power minus 2 whole square divided by 4 small n. Small n is also given, that is 10, and r is 100 means 1 meter. So if we put these values on your calculator, then finally you can get the answer as nothing but 5890 into 10 to the power minus 10 meter, that is therefore 5890 angstrom. So you see here the numerical is very simple, means all the values are given, you just have to put the values on the formula, then you can get the corresponding lambda. So if we do the summary, then what the numericals we have done today, first is I equal to I1 by I2 equal to A1 square by A2 square, that is intensity is proportional to the amplitude square. So therefore if we put the values, then Imax by Imin we are getting as Imax by Imin equal to this one. So here the formula we have to remember as the intensity is proportional to the amplitude square. Now on the next, if we go here, then it was in a double slit experiment. Okay, in that case this formula xn equal to n lambda capital D by 2 small d, this is a condition for maximum intensity. Then n maximum x maximum 10 is equal to this, and also here tan phi maximum 10 equal to this. So finally this is the condition for minima, 2n minus 1 means odd multiple lambda capital D by 4 small d. So distance x minima 1 equal to lambda capital D by 4 small d. So finally we are getting the angular position of first minimum as x minimum 1 by capital D. So here finally this is the angular position of the first minimum. Now next one is in a intensity experiment, the diameter of the 15th ring was found to be 0.59 centimeter and that of the 5th ring is 0.336 centimeter. So if we do the actually this derivation we had done in our theory, so if you do the practice then you can get it easily, where r is the radius of curvature of the plano-convex lens and n is the order number and d is the diameter of the ring. So if you put these values here, then finally you can get the corresponding wavelength of the light, that is your lambda, and the final answer we are getting as 5890. So by doing these three numericals, one thing is sure, that we must have to first have to go through the theory. If the theory is not clear, then we cannot do any numerical. Okay, so you must do the practice, and if you have any query, any question regarding any theory or any problem, you first try to be clear on that theory first. Okay, so if the theory is not clear, then you cannot get this numerical. So thank you for today, and if you have any question, any problem regarding any numerical, any theory, then please feel free to ask.